Welcome. This is part 4 of Lecture 1, Introduction to Algorithmic Thinking. We're going to start off with a motivation for why we are covering the topic of algorithmic thinking, and also describe in some detail what it is. We're then going to go through an algorithmic thinking example focused on univariate optimization. Finally, we're going to have a Matlab demonstration where I go in and implement this example and show how we can actually solve this optimization problem using Matlab code that we develop. Algorithmic thinking is creating, or the ability to create, an executable code from a process concept. At least this is the definition that I'm using here. When we learn, derive, or create a new algorithm or process, how do we take this conceptual understanding of the process or a mathematical description of this process and transform it into executable code that we can use for something useful? For example, here is an iterative formula that takes the form of many algorithms we're going to use in this semester. We're going to have this sort of formula where at iteration k is an index that says what iteration we are at in an iterative algorithm. We start at a point, say design x at iteration k, and then based on some kind of information from this point x at iteration k, we take a step. We take a step in some direction, and then we add these two numbers together, whether they are scalar numbers or vector numbers, and then that produces the new updated version of x k plus 1, or the value of x at iteration k plus 1. We're going to spend quite some time figuring out, for a number of different algorithms, how do we actually decide what this step should be. And there's going to be a process to that. And once we work through the concepts of that process, how do we translate this understanding finally into code that we can actually run? In this class, we're going to focus on Matlab, that we can actually run in Matlab. So here's an example of one of the algorithms that we're going to learn about in the section on unconstrained optimization. How do we actually go from an iterative formula that might look something like this, with some additional definitions describing how we take this step, into something like this that has enough information, enough detail that Matlab can actually execute it? Let's talk about algorithm development and how algorithmic thinking fits into this when we are working on the process of algorithm development. We need this skill, or this ability to think algorithmically, so that we can go from a conceptual description of an algorithm to usable computer code. And the intermediate steps in this process may vary depending on a number of different factors, including the complexity of the algorithm that we are working on. So for example, we might use an informal approach for simple algorithms. We could be as informal as simply just keeping everything in our brain. We can have a mental model for how this algorithm should work, and then we can translate that into code that we type out ourselves based on this mental model. But there's definitely a limit to the complexity of the type of process that we can really fit into our brain and manage at any given time. That's just the nature of the human mind. And so when we want to expand our work to more complex algorithms, we need more systematic approaches. So if we take a more formal approach, then it expands our capabilities. We can then venture into more complicated algorithms that may have some advantages over the simple algorithms that we are limited to when we're using informal approaches. So when the algorithm complexity is high with respect to human cognitive ability, it may be helpful to use a more formal approach. And today we're going to go through one possible approach that's a little bit more formal, where we're going to start off with a conceptual description where we describe the process we want to implement in words, and then we're going to translate that into a logical flowchart. We're going to formalize this description of the procedure and visualize it in a flowchart. And once we get it into a flowchart form, then it's easier to convert it into actual code. But the flowchart is really helpful for many people cognitively to understand the flow and logic of an algorithm. So why focus on this skill of algorithmic or computational thinking? In this class, we're going to be working through a number of different algorithms, both for optimization and other numerical tasks that are important for solving engineering design optimization problems. And this skill of algorithmic thinking expands well beyond just this course, of course, but we do need to have some level of algorithmic thinking skill to be successful in the tasks that we have in this course. We want to be able to automate the execution of some of these codes. Well, sure, we could just by hand walk through the steps of an algorithm, do all the calculations by hand, but that's a relatively slow process, and a lot of the algorithms we're going to work through is very easy to get these into code so that we can automate what makes sense to be automated, and then we as the human engineers, we can focus on the creative things that are more important to have the humans focusing on. We're going to see several different approaches for developing different kinds of algorithms, including optimization algorithms. We're going to see some heuristic strategies or more ad hoc algorithms that are not really based on some type of mathematical development. So, for example, genetic algorithms or evolutionary algorithms. We are going to go through other algorithms that are more theory-based. So we are going to derive mathematical optimality conditions that will serve as the foundation for the derivation of other algorithms. And as with many other numerical methods, some of the optimization algorithms we're going to derive are going to rely upon Taylor series expansions and iterative formulas like we saw a few slides ago. The ability to translate a conceptual process into code is a very important skill to develop for this course, SE 413. So it's a really good idea for you to invest early on in the semester to make sure you have this skill so that as we move on and start learning new algorithms, you can focus on the deeper concepts of the algorithms and be less worried about how to actually implement it in code. Algorithmic thinking and Matlab demonstration. Let's have a look at an example that involves univariate optimization, or in other words, a function. We want to find the minimum value of a function, but the function has only a single scalar input to that function. In this algorithmic development process, we're going to start with a description of the procedure in words. We're going to move on to formalize the process as a flowchart, and then from that logical flowchart, then it's pretty straightforward to construct the code that will execute this algorithm. And when I talk about a flowchart, this is something that if you've not used in a formal way before, you might want to do a little bit of digging. There are some standardized symbols that we use in flowcharts. For example, a certain type of block is used when it's time to make a decision, and we can go one direction or another. So before you start using random shapes in a flowchart, I'd recommend having a look at what are some of these standardized symbols that are used in flowcharts, and some of this information is available on the course website. We're going to consider this task of minimizing a continuous univariate function and address this question of, can we follow this process, including an intermediate step of creating a flowchart, to develop a minimization algorithm in Matlab? given the ability to evaluate some function f of x and the assumption that f of x is a smooth, continuous function, continuous meaning there are no creases in the function, the first derivative is a continuous function, we want to propose, implement, and demonstrate an algorithm that can find a value for x that minimizes f of x. Here's a plot of the example function we're going to be using today, and clearly there is a minimum over here just to the left of 5, and we want to create an algorithm that can find this minimum. We're going to use this concept of bisection. Here I'm going to introduce the concept, and then we're going to step through a few different stages where we gradually increase the level of formality until we finally get to actually writing the code that's going to implement this bisection algorithm. The first step is to define a bracket, which is a range of values in the function input space between two limits. So we want to define some bracket that encloses some domain in this input variable space. Suppose I have a lower limit of -5 and an upper limit of +7, for example. That could be one possible bracket. And we can then check the sign of the function slope at each of these limits. And if on one side it's negative and one side it's positive, that gives us some important information about what the function might be doing in between, especially if we are assuming that this is a continuous, smooth function. If the sign does change, then the bracket must contain either a minimum or a maximum. This statement is only true in cases where we have a smooth continuous function. If we had a discontinuous function, then we can have an instantaneous jump in between the bracket, and we could have this change in sign without having a minimum or a maximum. Let's restate this mathematically in a little bit more rigorous way. Suppose we have this continuous function f of x that is a mapping from the one-dimensional or the set of real variables that are one-dimensional that maps back to the set of real variables that are one-dimensional. And suppose we have these two values in the domain of f of x that serve as our limits, that define the bracket that we're using in this algorithm. xa is our left-hand bracket, and that is strictly less than xb, which is our right-hand bracket. And suppose specifically that we have the corresponding derivatives of this function at xa and xb such that at xa the derivative is negative, strictly negative, and at xb the derivative is strictly positive. Then in this case there is a point x star that must exist within the bracket xa xb that minimizes f of x. And I can state this definitively because of the order of these signs. So we have a negative slope at the beginning at xa, and then at xb we have a positive slope. We have a decrease and then an increase. So therefore somewhere in the middle we must have a minimum, and that requires this assumption that the function f of x is continuous and smooth. Given these observations about a bracket enclosing a minimum, what kind of procedure might we use to find the precise location of the minimum x star? Thinking back to Calculus 2, which you probably took either in high school or your freshman year, there is a section typically that's covered on function minimization. Can you recall what must be true for a point x to be a minimizer of a function f of x? You might think back to this requirement that the derivative of f of x must be equal to 0. But remember this question: if the slope at a point is 0 Must it be a minimum? Or could it be something else? Are there some other possibilities? Yes, there are other possibilities. It could be a maximum or a saddle point. And when we think about the slope being 0, one way of interpreting this graphically is at a point x, if the slope is 0, then the tangent line to the function curve must be flat. It's horizontal. And there are 3 different ways that can be the case. We can either have a minimum, a maximum, or a saddle point. And a saddle point, we're going to learn more about this later in the course, but the saddle point is basically where we come to a flat spot. Say we're decreasing from the left, we come to a flat spot, and then we go back to decreasing. We could have a slope of 0, but not be at a minimum. What condition, in addition to 0 slope, is required to guarantee a point is a minimum? There actually are multiple ways of making this guarantee, but you may remember from your second course in calculus that if the second derivative of the function is greater than 0, then yes, we can assert that this in fact is a minimum, not a maximum or saddle point. So we need the second derivative information, the second order information or curvature information to make an assertion about the nature of this point that has a 0 slope. Let's go back now to thinking about the bisection strategy, which is part of a larger class of numerical methods called bracketing methods, because it relies on a bracket, a lower and upper bound that describes some domain of interest in this case, the input variable to the function f of x. So here, suppose we have a bracket, xa, xb, and at the left-hand side, the slope is negative, and the right-hand side, the slope is positive. And then if we go to the midpoint, or the point that's halfway between xa and xb, and we can compute that here just using this formula finding the average of xa and xb, then we can compute the derivative at that point. Then it gives us some really important information. We take that midpoint, we form 2 new brackets, a left-hand side and a right-hand side, and then if we have this piece of information, what is the sign of the slope at the midpoint, that should be xm, not xa, then that'll give us some information about what side of the midpoint the minimum is going to be in. And so this gives us a strategy of honing in on where the minimum is. In the next slide here, we're going to visualize what's going on here. Suppose we have some continuous, smooth, objective function. And suppose we have one bracket defined by xa and xb. And if we look up here, these green dots show what the function value is at each of those points. And within this bracket xa, xb, we can visually see that yes, there exists a minimum right about here, but we want to formalize this. Here's the value of the function at xa. Here's the value of the function at xb. And we can see just graphically that the minimum is right here. We often use this symbol x star, subscript star, to indicate that we are at a minimum. And we'll see this in some of the development later in the semester, but this is just some of the notation that's helpful to get accustomed to. Suppose we then calculate where the midpoint is, denoted here by xm. And at this midpoint, then we're going to be interested in calculating what is the slope at this midpoint. And we're interested in an algorithm that can help us really zero in on where the minimum is with limited information. If we are visualizing this function as we are doing here. This actually requires a tremendous amount of information. To get a smooth plot like this, we might need hundreds of different function evaluations across the domain here of the input variable x to get this smooth representation. That's a lot of information. We want to find the minimum x star while limiting the number of function evaluations that we need to make. After bisection, if we were to at least visually inspect where the bracket is, it's very clear that it's going to be in the left-hand side. So how can we define some condition using limited information to make this determination without having to evaluate the function at many points, as is the case if we are doing visualization? What condition must be true for a minimum to be in a bracket? As we pointed out before, the function derivatives at the bracket points must have opposite signs. So if we're considering two different brackets here, xa, xm is the left-hand bracket and xm, xb is a right-hand bracket, we want to see which one of those has different signs. So xa has a slope that's negative. xb has a slope that's positive. So within xa, xb, we are going to have a minimum. But then at xm, we can see visually, oh, well, that's positive. So if we're looking at the right-hand bracket, xm, xb, there's not a change in sign. We go from positive slope to positive slope. So we can't really say that there is a minimum within that bracket. But on the left-hand side, we're going from a negative slope at xa to a positive slope at xm. And then we can assert that there is a minimum within the left-hand bracket. The next step then is to address this question of how can we use this condition, this knowledge about how to use limited information and this bracketing strategy to derive a procedure that iteratively increases the accuracy with which we approximate the minimum x star. The basic idea is we want to get closer and closer to this value of x star. And if we were looking at this in a more mathematical way, we'd want to be able to show or prove that as the number of iterations, as that marches off to infinity, the accuracy of our solution converges to the true solution. What we want to do here is, once we've defined this conceptual process, bisection, where we use this observation about a change in sign of slopes to decide what side, the left-hand side or the right-hand side, the minimum is going to be in, and then iterate and keep reducing the bracket size. We want to extract the logic behind this process and then formalize that procedure. So recall from earlier, we start off with a description of the procedure in words. We've done that. We've also included some graphical illustration. But then the next step we'd like to take is to formalize this as a flowchart and then implement this as Matlab code. Can we follow this process now then to develop a bisection algorithm in Matlab? Let's go through a conceptual description of the overall algorithm here for bisection for univariate function minimization. First, define a bracket where the sign of the slope changes. Then, divide the bracket in half. Check which side contains a slope sign change. Assign this side to be the new bracket. Iterate until a minimum bracket tolerance size is satisfied, or until the maximum number of iterations is exceeded. Or in other words, if we set a really small value for this tolerance for the minimum bracket size, then this process, if it's successful, is going to keep going, iterating until we keep shrinking that bracket size until we hit this tolerance. And then we can set this ahead of time to be the the accuracy with which we find the solution. But as with most iterative algorithms like this, we need to have some kind of safeguard in the algorithm so that we don't end up in a loop that just keeps going forever. And so a typical thing for us to do is to keep track of the number of iterations and then to set a maximum number of iterations that are allowed for a particular algorithm. Here's a conceptual check. If we go through this process, what can we say about the resulting point? Is it going to be a minimum or possibly something else? Recall there are three different possibilities if we have a point where the derivative of a function is equal to 0. We can have a minimum, maximum, or a saddle point. Here, at the beginning, the starting point just indicates that we need to define a bracket where we have a sign change in slope. We did not indicate what the sign needed to be on the left-hand side or the right-hand side. So what if we had a starting bracket where the left-hand sign, derivative sign was positive and the right hand was negative? Then we're going to have a maximum in between. So we need to pay attention to details like that as we go through algorithm development. Assume these two things. We have a continuous, smooth function, and we have a bracket that encloses a minimum. And in this case, we are making the specific assumption that the sign of the derivative on the left-hand side is negative, and the sign of the derivative on the right-hand side is positive. Step 1, calculate the midpoint location. Step 2, check the derivative, and if it's 0, we're done. Then we are at the minimum. We're at the minimum because we have the specific assumption about what the signs were for the ends of the bracket at initialization. Step 3, if at the midpoint the derivative is greater than 0, then the minimum is in the left-hand bracket, or xa, xm. If instead the derivative at the midpoint is negative, the minimum is in the right-hand bracket, xb, xm. After we've done this check, we then need to update the bracket to be the half-size bracket, one of these two brackets that contains the minimum, depending on the sign of the derivative at the midpoint. Then we repeat this procedure. We go back to step 1, calculate the midpoint location with this new bracket, and keep repeating until either the bracket size shrinks below a predetermined minimum, a tolerance value that we set, and that's the ideal outcome, or a maximum number of iterations is exceeded. If the maximum number of iterations is exceeded, and that's the reason for termination, then we don't really have a guarantee that we've found a minimum. Here's a quick conceptual check. I've probably already given it away. In this case, what can we say about the resulting point? Is it going to be a minimum? Yes, because of this additional assumption that we made that the starting bracket has these specific signs. If we go through this particular process with this starting condition, and we have a continuous smooth function, then yes, we are going to have a minimum resulting. Now that we've gone through these first few steps, we've made these observations about bracketing methods and the basic concept behind bisection and having a look at the derivative of the midpoint, and then we, in words, described a little bit more formally how this iterative procedure could occur. Now we can get into the flowchart. We're going to formalize this step by step and see how this logical flow works. And then once we have this established, then it's going to be a lot easier to go from the flowchart to the actual code in Matlab, as opposed to just going from the concept of bisection directly to the code in Matlab. So this intermediate step for more complicated algorithms can often be useful. The first step here in this flowchart is to initialize the problem. So we need to define what is the bracket, what's the left-hand limit, what's the right-hand limit, what's the bracket tolerance, how small do we want the bracket to be before we terminate the algorithm. Let's set the iteration counter. So when we're starting the algorithm, maybe we set k to either 0 or 1, and then each time we go through the process, we increase k, we increment k, so we can keep track of the number of iterations. And then once we set this maximum number of iterations to some integer value, we can compare k against this limit, max iterations, and see if we need to terminate or just keep going until we've satisfied this tolerance. Okay, once we've done this initialization, we check first, is k, the iteration number, greater than the limit, the maximum number of iterations? If it is, we're done. And this, of course, is not going to happen on the first step unless we've defined the maximum number of iterations to be 0 or 1, depending on how we initialized k. But at later stages of the algorithm, when we go back to this step and we check k, this is where we could terminate because we've just iterated for too long. If we've not exceeded the maximum number of iterations, then we check the bracket size. What is the distance between xa and xb, and is that distance less than this bracket tolerance? And if it is smaller, then we're done. And this is the successful termination. This is the case where we have successfully shrunk the bracket size to a value that's small enough that we are happy with the accuracy, or we're close enough to the value of the true minimum. So this is the result. This result is the approximate minimum, and the midpoint is what we report as the approximate minimum. If we have not shrunk the bracket to a size that's smaller than this tolerance, then we have a look at the derivative. We ask the question, is this equal to 0? And if it is, then, well, we are at a point that if we have an initial bracket where the slope is negative on the left-hand side and positive on the right-hand side, then we're definitely at a minimum. If we had some other initial conditions, then it might be either a maximum or it could also be a stationary point, possibly, if we have this derivative being equal to 0. So this is a successful termination case as well, but as we're going to learn later when we go through the section on numerical methods and optimization, numerical foundations, we're going to see that satisfying this very specific requirement is going to be a pretty unlikely thing in the case of using a digital computer where we have discrete representations of numbers, and in most cases we're using some type of, or we're using a floating point number representation scheme. If the gradient is not exactly, derivative is not exactly equal to 0, then we go to this next step. We check and see, is the derivative positive? If the derivative is positive, then based on the description of the procedure in the last slide, we can then assert that the minimum is in the left-hand bracket. If it's in the left-hand bracket, then we reset the bracket. We will reset our value of xb, the right-hand side of the bracket, to be xm, the midpoint. And so we've basically just converted our bracket from the full-size bracket to the half-size bracket, specifically the left-hand half-size bracket. And then we go back up here to the top and we go through this process again and go through the next iteration. But we've not yet covered the case where this is not true. So if it's not equal to 0 and it's not positive, then what's the other possibility? Is the derivative less than 0? If yes, then we have the minimum in the right-hand bracket instead of the left-hand bracket. So then we set xa, the left-hand limit of the bracket, to be equal to the midpoint. So now we are choosing to update the bracket to be the right-hand half-size bracket. Once we've done that, then we can go back to the beginning. One question to ask here, just to think about, I'm not going to answer, are there any other possibilities, any other outcomes that we've not considered here? When we are developing algorithms, it's important to make sure we work through and articulate all of the possible outcomes as we are going through logical flows like this. So as you are setting up flowcharts as an intermediate step, please be sure to make sure you've exhaustively thought through all of the possible outcomes. If you don't, and you happen to test your algorithm in a situation that exercises some of these unanticipated outcomes, then you're going to get an unexpected result that could either be erroneous or maybe the code actually fails. Now we're going to go through this and see how to actually implement this in Matlab. We want to translate the logic that is embedded in this flowchart into Matlab code. And as we go through this, we're going to pay attention to things that could cause failures in the code, and we're going to build in some safeguards into the code, or some error checks. Here's a visualization of what we are aiming for at the end. Here's the test function, this blue line. We want to find the minimum of this blue line. Also, another thing we use along the way is the derivative of this function, and the green line here, that is the derivative of the function. This dashed black line, that shows where the function value is 0, and we can see this green line here is negative most of the way until we get right there. Then it crosses 0, and then it goes positive. And where this green line crosses 0, that's where the minimum is. Let's switch over to Matlab. Here's the Matlab command window. I'm just going to do a little test here, assigning the value 1 to the variable x. We can see that over here in the workspace we have x and with the value of 1. And I'm going to start off our file, our M file, this script that's going to execute the bisection algorithm using these commands, clear and CLC. Clear clears the memory. It erases everything that's in memory right here, and CLC clears the screen. This is a pretty typical thing that I like to do at the beginning of many of my MATLAB scripts, unless I have a specific reason not to. So if I click Run, I can see that we've cleared memory and we've cleared the screen. We can also run this in a different way. Say, let's put x into memory again. I've named this file bisectionexample.m, and over here we can see that yes, I have this file in our current folder, or the working directory. So if I were to type bisection example, and here I'm just going to, I just hit tab, and Matlab went through and did a search on the path to find functions that start with these 6 letters that I first typed, and it found 2. So it has a built-in function, and then it has my bisection example, and then I hit tab again, and then it auto-completes, and I hit return, and it executes it. Oh, and I've actually here, I guess I left a debug point right there. So it actually didn't execute the whole thing. It stopped at that line. And this is a really important skill to have to learn how to use this debugging. We are in debugging mode. The command prompt looks a little bit different here. It has this K right here. And this allows us to do some interactive things while we are still in the middle of the execution of a code. It's debug mode. So here I'm going to just click Quit Debugging. I'm going to click this circle to clear the debug point. I'm going to click the up arrow to recall from my command line history bisection example, run it, and now it did not stop at the debug point. It did execute clear CLC. Not sure why that came back up again. And now we have a clear screen and a clear memory. Let's define the function we want to minimize. And here I'm going to use the anonymous function capability in Matlab to do this. And so I'm going to type f. That's going to be the variable that essentially points to the function. And I'm going to say at x. So this tells us, the at symbol tells us this is an anonymous function, and everything I put in the parentheses, that represents the input arguments. And when I define the anonymous function, this is essentially a dummy variable. I don't have to have x defined up above. I just show how x, or whatever the input argument for the function f, I'm going to show in the rest of this definition how it's going to be used. So this test function is x minus pi, and pi, that is a built-in constant in Matlab, quantity squared. And I'm using this dot operator that allows us to do element-wise computations. And this is something that's super useful for vectorized calculations, or allows Matlab to really fully utilize its strengths with matrix calculations. We're going to learn about this a little bit later on in some more detail, but I recommend that you look at this element-wise calculation operator, or the dot operator here. And then the second term, 4 times sine of x. I'm going to add the semicolon to suppress the output. And now I'm going to do a few things related to plotting. I'm going to define what are the limits of our plot. What are the minimum and maximum x values that we want to show in the plot for visualization of this function. We're going to go from -10 to 10. And then I'm going to use this figure command. This is going to open a new figure window, and it's specifying that this is going to be figure 1. And then I'm going to use the clear figure command CLF. This tells Matlab to clear all of the contents of figure 1 if figure 1 already exists. If it doesn't already exist, if figure 1 does not already exist, then the CLF command is not going to do anything. Okay, now I'm going to use the fplot command. There are a number of arguments of fplot, and if you want to know what the syntax is for a Matlab function, you can just type help and then that function or command name, and it steps through this succinct documentation just right in the command window. And to use fplot, we at least need a definition of a function that we would like to plot. And it needs to behave in a way that works well with fplot. And it gives some examples down below as well. So here we're using this anonymous function format, and so that I hope soon will become familiar to you. We can also specify what the limits are. We can specify what the line specifications are, so things like weights and colors and that sort of thing. And then if we specify that there is an output of fplot h, it returns a handle to the function line object created by fplot. Without getting into a lot of detail about what that means specifically, is if we save in this variable h the object created by fplot, that allows us to go back in and do some really powerful things with the figure that we've created with fplot after we initially created that plot. So we're going to start off with a symbol, a variable. I'm going to call it h1 for handle for figure 1. And that's going to allow us to do some useful things in a few minutes. And we're going to start off with the first input argument, f, that we've defined up above. That is this function that we defined as an anonymous function. And then we want to define what the limits are for plotting. And I started typing out p-limits, but I can just click tab here, and that'll auto-complete. And so that helps speed things up. And then here we can give some information about the line, the curve. What is it going to look like when we plot it? I want it to be blue, and I want it to be a solid line. And then I can also specify right after that really any number of line specifications just separated by commas. And in the Matlab documentation, you can look up what the specific commands are for these different things you have control over in various plots. And so line width is one thing I want to adjust. I'm going to increase it. The default is a line width of 1 point. I'm going to increase it to 2 points. Now there's an interesting thing. I'm going to use this command called hold on. And if you're interested in learning more about that, just type help hold, and it tells you how it behaves. If we don't use this, and if I were to use another plot command, and I wanted to have it plot on figure 1, it would just erase and overwrite everything. But if I want to plot multiple things on the same figure, then I can use this hold on command. I'd like to create a label for the horizontal axis. Here, that's defined as x label. I'm going to call that the optimization variable value. And then I'm going to give it a title, this figure a title, Bisection line search demo, or short for demonstration. Okay, so we've gone through and created a way of plotting this function that we've defined up here in line 3. Let's test it out before we get too far in coding. Let's see how it works. So I just clicked run. Here we have a blue line of width 2 that shows the shape of the function that we'd like to minimize. So things seem to be working well so far. As part of our algorithm, we're going to need to know what the derivative is. In this case, we have a very simple function, and we can just apply basic calculus techniques to analytically derive what the derivative of this function is. In general, if we are using something that's a more complicated formula, or maybe it's a simulation or some type of approximation that actually calculates the function value, then we might not be able to apply calculus very easily to calculate or symbolically derive what the derivative is. And we're going to learn pretty soon how to calculate estimates for derivatives using numerical strategies. And those are going to be important for practical applications, many different practical engineering design optimization problems. Here in this case, though, we can define the derivative. I'm going to use the symbol df to represent the derivative. Again, this is going to be an anonymous function, and that's going to be equal to 2 times x minus pi plus 4 times the cosine of x. And now we can plot that. We've used the hold on function, and so if I use fplot again, it should show both the function and its derivative on the same plot. So we want to plot df using the same limits. And I want to use pretty much the same options here, except I want to change the color. So I'm going to still have a solid line, but I'm going to make it green and have a line width of 2. This might be a good place to check our work again. I'm going to click Run, and now we can see that yes, it has plotted the green line, and that makes sense. I also want to add a 0 line so that for visualization it's easy to tell when we are positive or negative. To plot the 0 line, I'm going to use a different command, not fplot, but plot. This works a little bit differently. If we type help plot, instead of inputting a function, we need to input points. So we plot the vector y versus the vector x. And here, if I'm just defining 2 points, if I just define a point here at 0 on the left-hand side of the figure and a point at 0 on the right-hand side of the figure, then I can draw a line in between those 2 points and create a nice dashed line that's going to indicate where 0 is. So I want to have this go between the plot limits. So these are the x values of these vectors, and then I want the y value of each of those points to be 0. And I want a dashed line, and so the symbol for that is dash dash, and then I want it to be black. The symbol for that is k. And I'm going to leave it at the default line width. Let's run it. And there, it added this dashed line, so it's a little bit more clear. We can see where the green line crosses 0, and that's going to tell us where the minimum is. And if we want, we can zoom in and see that quite a bit more precisely. So we can see here, that's where the derivative is 0, and then this is the minimum. So I just double-click there to zoom back out. Now let's go into initializing the algorithm. Now that we've defined the function and its derivative, we're going to go to the first block that we saw in the flowchart. We're going to initialize the bracket. That's going to be -10 to 10. And if we have a look at figure 1, at the left-hand side at -10, the derivative is negative. And then on the right-hand side, at +10, the derivative is positive. So that fits our stricter assumptions. And because we have a continuous smooth function, then we know that there's going to be at least one minimum that occurs somewhere within that bracket. Now we need to do a check. Let's make sure we have a valid bracket. What would happen if B1 was greater than B2? Well, the rest of the algorithm that we're going to be developing is probably not going to work very well. If we assume that B1 is the left-hand side and B2 is the right-hand side, but B1 was greater than B2, that's going to cause some numerical problems. So here I'm going to use the error command. This is a command in Matlab that helps us to define our own errors, where we can detect whether something happens, and if it happens, we can specify a response. So here we're basically just going to be using this message ID. We're going to trigger this error message that will display to the screen what's going on. And that's what I'm going to do right here within the single quotes that define a character string. Bracket values must be in ascending order. And then we close, or we add an end that corresponds to that if. So now we have this these logical statements. Understanding logical statements in Matlab, that's a super important element to learn. And let's have a look at what's going on here. I'm going to add a debug point right there at line 16, and I'm going to click run. So it's going to run everything through 15 and then leave us at 16. And if I go to the workspace, I can see, oh, the vector b, it has this value of minus 10, 10. And so then I would expect that this b1 being greater than b2 is not going to be triggered. So what happens if I were to just copy and paste this into the command line? So we're paused now, and we can use Matlab interactively while we are paused. So is b1 greater than b2? This is a logical statement in Matlab. When we are using a logical statement, if it is true, it will output a 1. If it's false, it's going to output a 0. It output a logical 0. So it is not true. And when we're using this if statement, we are basically saying execute whatever is right after the if statement, or between if and end, if the expression right after the if statement is evaluated to be true. But here it's false, so we are expecting that it will not be evaluated. In the debug mode, we can go through, and instead of just continue and running, we can do this one step at a time. And so I'm going to click step. And one step skipped over line 17. And so we can see that, in fact, this did evaluate the logical after the if statement as expected. And then here I can click continue, and then it finishes, and we're done. It finished executing, and so we've gone back to the normal command prompt. What's the next step? Well, first I'm going to get rid of that debug point and move on to the next line. We'd like to evaluate the function derivative value at either end of the bracket. And I'm going to use the symbol df for the function derivative, b1 for the left-hand side of the bracket. And to evaluate that, we use this function df, which we defined up above, and we're going to evaluate it at b1. And then we're going to do the same thing, but I'm going to call that df b2, and then we're going to evaluate b2. And we can go ahead and run that, check our values. So the derivative is negative on the left-hand side and positive on the right-hand side. Let's actually go back and have a look at what happens if we do execute this code such that we trigger this error. If I were to define the bracket incorrectly, such that b1 is greater than b2, then we're going to see this error message pop up. First, I'm going to set the debug point, click run, and now we have b defined differently, 10 minus 10. And we can go ahead, and I'm going to pull up from the command line history this logical statement, is b1 greater than b2? And in this case, we have this logical 1, yes. So I'm expecting this error message now to be triggered. I'm going to click step, and yes, we stepped into this if statement. We've not executed the error statement yet. I need to click one more time, step, and now we have triggered this error. It tells us what function or what file the error came from and what line it came from, and then it displays the message that we indicated here with the error function. So now if I click run, it's going to go back to the debug point. So here I'm just going to click quit debugging, remove the debug point, click run again, and oh, well, yeah, of course, we still have the error. So I need to go back and fix the error. If we don't know exactly what the error is, one thing you can do is actually just click this line 17. That's a hyperlink, and it takes us right to the line where the error occurs, and so we can have a look at the logical statement or expression that triggered this error, and then we can go back and maybe use a debug point here to see what's going on before this that's causing the error. But here we know we just need to change it back to -10, 10, click run, and now we have results as expected, and we have the function derivative values there, the bracket points. Now we need to check and see if a minimum exists in the bracket. For the iterative nature of this algorithm to work correctly, we do need to have the case that we have a negative slope on the left-hand side of the bracket and positive slope on the right-hand side. So how can we check that in Matlab? I want to show how to construct a little bit more complicated logical expression to check that, and then again use that with the error command if this requirement is not satisfied. Here we have in memory all of these things that we're going to need to use to check this. We want to check whether the derivative on the left-hand side is negative and the derivative on the right-hand side is positive. And to do that, we can use this command called sine. So this function essentially just returns 1 if the element is greater than 0, and -1 if it's less than 0. And we can check the sign of these different values. So sine of df(b1). This we're expecting to be, this should give us -1. And then if I want to check 2, the right-hand side, that's going to be +1 because it has a positive sign. Now, how do we construct arguments that are going to test whether the left-hand side is negative and the right-hand side is positive? We want both of those statements to be true at the same time. So here I'm going back up using this sine command for the left-hand side, and I want to create this logical statement basically asking, is the sign of this derivative less than 0? Is it strictly negative? And if it is negative, then that should give us a logical true, and it is. And then we want to check whether the sign of the right-hand side is strictly positive, and then that should give us a logical 1 or true as well. But how do we check if both of these conditions are satisfied simultaneously? This is where we need to use the AND command, and there are actually multiple ways of implementing that in Matlab. And I'm going to here just use the word and we can do it this way. We want, so this example right here will take logical statements A and B, and if they are both true simultaneously, the AND function will return true. So for example, if I say AND 0, 1, this should give me false. But then if I say AND 1, 1, this gives me true. How do we apply this to checking the sign of the ends of the bracket simultaneously? Let's go back and use this command, but we're going to use the AND command. We want to see if the sign is less, or the sign is negative on the left-hand side, and the sign is positive on the right-hand side. And it is, so that's good. And we want to keep going if that's the case. We only want to stop and trigger the error message if that's not the case. And so that's a clue to the next logical function we're going to use, and that is not. So if I type help not, this essentially just switches true to false and false to true. So if I type not 0, that'll give me a logical 1. If I type not 1, that's going to give me a logical false. And if I go back up to this original compound statement, and this is true, we want to keep going if this is true. Or in other words, we only want to trigger the error command if this is not true. So I'm going to use the not there. I'm going to wrap that around it, and that's 0. And that's what we expect. So I'm going to copy and paste this over into the code, into a new if statement. If this whole expression is true, then that means we've not satisfied the sign requirement for the derivatives, and then we need to throw this error, and I'm going to say the minimum may not be contained in the bracket. Okay, so run that. No errors, as expected. But what if we shift things a little bit? What if we choose a point such that a minimum is not contained? What if I keep the right-hand side at 10, but what if I say the left-hand side is 8? There's no minimum there inside that bracket. So I'm going to change this minus 10 to 8, and I'm expecting an error to be thrown. Well, an error wasn't thrown. Can you see what I did? It was a pretty easy mistake. So there are actually two different places in the code where I've defined limits. These are p-limits. This is not the bracket. I want to leave the plot alone. So I'm going to go over here and redefine the bracket, not the plot limits, and rerun it. Okay, so we have this plot, and we did throw this error as expected. The minimum may not be contained in the bracket. In this algorithm, we're going to be iteratively checking the bracket size. And when the bracket size gets small enough, then we're going to terminate. But to make this work, we need to find an initial value for the bracket size. I'm going to use this variable b size to be the bracket size, and that's going to be equal to b2 minus b1. And I can do it this way because we've already checked that b2 is greater than b1. Otherwise, we could use the absolute value function or the norm function instead. And I'm going to initialize the iteration counter to 0. That's another thing that we need to keep track of as we're going through this algorithm. We also need to specify some algorithm parameters. We talked about a tolerance, a limit for the size of the bracket. As soon as we get below this tolerance value, then we're going to terminate. And in using the Matlab notation for scientific notation, this is 1 times 10 to the minus third, or 0.001. That's going to be the smallest bracket size that we're after. And then I need to set the maximum number of iterations, and I'm going to here just specify that as 100. Now, to go through this loop that we defined in the flowchart, we are going to use a while loop because we don't know ahead of time how many iterations are required. If we knew ahead of time how many iterations were required, we could use a for loop instead. But we don't, so we're going to use a while. You can get information about the syntax for while here. So while some expression is true, execute all these statements between while and end. And part of these statements could be updating things that feed into this expression. And so this expression is not always going to be true. But if this expression, we have to have safeguards. So we need to have a maximum number of iterations specified within that while loop. So let's define the bisection while loop. While something is true, execute some statements, and then there's the end that corresponds to the while. So there are two things we want to track. We want to keep executing this while loop while the bracket size is larger than the tolerance and k is less than the maximum number of iterations. The key word there was and. So I am going to be using this logical function and. I'm going to check first, is the bracket size greater than the tolerance value? And is the iteration number less than the maximum allowed number of iterations? So if both of those things are true, we're going to keep iterating, but as soon as one of those becomes not true, then the and expression here, or this statement, is going to be false, and then the while loop is going to terminate. So we've initialized both b size and k. So now we can actually get into the guts of the algorithm. And because I started k at 0, I'm going to do the k increment right here, k equals k plus 1. For those of you who are accustomed to C or C++, we don't have the k++ command in Matlab. So I just have to manually define k equals k plus 1. Now we need to have a look at the midpoint. I'm going to use xm to represent that, and that's going to be equal to b2 minus b1 divided by 2. That's the midpoint location, and I want to find out what is the derivative at the midpoint. So I call the derivative function and evaluate that at the midpoint. And while we're going, it actually would be nice to plot things as we go, and we can see how the algorithm progresses. It can help us get a better conceptual understanding for what's going on. And this actually can be a really helpful debugging tool if we're struggling to figure out what the cause of some problem is. So if you're inside of a loop, maybe you can use some type of plot to visualize the relationships between different numbers. I'm going to use the plot command here. I'm going to plot as the x values b, let's see, and then 0, 0, and a black diamond. And now I'm going to plot at the locations b the function value at b. So these first two arguments for the plot command, these are the x values for 2 points and then the y values for 2 points. And here I defined it pretty compactly. Here I have b, this defined up above, gives me the left-hand bracket and the right-hand bracket. And then f of b, this will actually output both simultaneously. I'm going to demonstrate that right here. I'll put well, actually first I have to finish this. Either finish this line or comment it out. And now that I've put that debug point there, I can show you how f of b works. So I'm just going to clear the screen here. So there's b as expected. And that reminds me, I need to go back and change the bracket. But if I have a look at f of b, and b has two components to it, but f is a function of only a single variable, what's going to happen? Well, this gives me a vector valued output. And the really cool thing about this, or why does it do that, is because I use the dot command, this element-wise operator. If I had not done that, I would have received an error. So I just removed that. I still have the debug point in the same place. I'm going to hit run. Warning, function behaves unexpectedly on array input. So basically Matlab is passing in this array b into f, but f is not defined in a way that works well with arrays. But if I put that dot in there, that means it can just calculate this function a bunch of different times for a whole array of different input arguments, and then give me a whole array of corresponding output arguments. We've had a look at how that works. Let's get rid of that debug point. Plot b f of b, and I'm going to use black circles for the right-hand bracket. And then it would also be nice to plot the midpoint. And here xm is a single value, it's a scalar, and we're going to plot a point on the horizontal axis, so y equals 0, and I'm going to plot that midpoint as a red plus symbol. And then plot xm f of xm, and then this again is going to be a red plus. We have calculated the midpoint, we've calculated the derivative at the midpoint, we've done some plotting to help with visualization. Now we need to check a number of things. We need to check the information that tells us where the minimum is going to be. And so we're going to use some if-else statements here for that. I'm going to first check, and remember this was the first check that we did at the, thinking about the bottom slide of the flowchart toward the bottom, we were checking, is the derivative equal to 0? So is the derivative at the midpoint equal to 0? Notice I use this double equal sign. That is when we want to use equals as a logical operator. If that's the case, we're going to stop the loop. We're going to break out of the while loop because we're done. Else, if the derivative at the midpoint is strictly greater than 0, then the minimum is going to be in the left-hand bracket. And so therefore, I set b2 equal to xm. Else if dfm is strictly less than 0, then that tells us the minimum is in the right-hand bracket. And so then I need to make the left-hand side of the bracket equal to xm. And then I can end that if-else evaluation, and now I need to update what b size is, and that's going to be equal to b2 minus b1. Okay, and let's go back up and make sure, yes, the plot limits are good. Oh, I should change that so that we have a valid initial bracket. And I have a couple of additional things to add. I'd like to put a legend on the plot, so we can use a legend command, use help, or look up the documentation if you want the syntax on that. So here we have these two different handles that we defined using the plot commands up above, and I'm going to label the first plotted curve as f of x, and then the second plotted curve as the derivative of x. And now I'm going to compile the results. The optimum we're going to report as the midpoint. So the midpoint at the end of our iterations, that is our approximation for the optimal value. And then I'd like to know what is the function value at the optimal value. And so I just evaluate the function at the optimum. And then just for fun, I'm going to ask at the end, why? Okay, let's go through, see if I made any mistakes. I'm going to click Run. I don't see any error commands. Let's see. So I do see, yeah, I wonder what's going on there. I don't think things are working quite right because I don't see midpoint markers at the minimum. But we do have an answer for why. The bald and not excessively bald and not excessively smart hamster obeyed a terrified and not excessively terrified hamster. Maybe, I don't know if that's a good answer. I should ask why again to fool the tall, good, and smart system manager. So there's an interesting bit of history. This is part of how Matlab was developed. This is one of the test functions that was created early on. And you can have a look at how y is defined if you click Edit Y. And it is designed to produce answers that are grammatically correct, but it has a lot of randomness to it. And so here are all of these different possible elements of the answer that could be in there. So if you ask why again, you're going to get a different answer. And you may get some repetition. But you know, so far I have not seen the answer to why be 42 yet. And I'm not quite sure why they didn't include that as an answer. I think I see what's going on. I see the mistake that I made. The midpoint needs to be defined as the average of B1 and B2. But on line 35 up here, I made a mistake. This is supposed to be B2 plus B1 divided by 2. Perhaps because I was thinking about the bracket size formula, I needed B2 minus B1. I need B2 plus B1, or B1 plus B2 equivalently. So let's see. So I'm going to quit debugging, turn off that debug point, and run it and see if it works. That is so much better. That is much more what I expected. So we can zoom in and see what's going on closer to the minimum here. And yeah, we can see it's clustering around right where the derivative passes through 0. And we can see in the command line what the optimal position is, 4.17. I can have a look at what f opt is, minus 2.36. And I can also check the derivative at the optimum, and that should be really close to 0. And at least within the bracket size tolerance, we did a pretty good job getting very close to 0 using this very simple approximate algorithm. Let's go through and actually use some of the visualization. I'm going to close that window. I'm going to go back here and put a breakpoint. I'm going to do it here at the end of this while loop so that we pass through these plot commands at each iteration. And I'm going to click Run, and I'm going to expand this. So now you can see at our first iteration, here's the midpoint, here's the function value at the midpoint. And you can go through and just click step if you want to just do one step at a time, and you can calculate, or you can see, like I'm hovering, there's the new midpoint, step again, there's the new derivative value, and then step, plot, plot. So now we have this new midpoint over here at 5, and that's actually quite a bit closer. I'm going to zoom in a bit here. We're starting to already get very close to where the minimum is. Now, I don't have to step one line at a time. I could just click continue, and that's going to run until we hit the breakpoint again. So I click continue, and we can go back and visualize what's going on. So we have more red points, and we can see how they are gradually getting closer and closer to the minimum. So you can just step through one at a time. I'm going to zoom in again, and this time very narrowly. And you can see we're already really quite close to where the derivative passes through. I'm going to click continue, and it's going to keep going. But it looks like now we have satisfied the tolerance. We can see how many iterations were required, and k is equal to 15. We could try doing some adjustments. I can turn off the breakpoint. I can change the tolerance, perhaps. What if it's 1 times 10 to the minus 4th instead? So I turned off the breakpoint, so it's just going to go through without pausing, and we can see what happens. We can see what the derivative is at the optimum. We get a more precise value, how many iterations were required, just a few more iterations, just 18. So that's actually a pretty good algorithm. We can go 10 to the minus 6th even and run it and see what the accuracy is. Really good accuracy in that case, and k is equal to 25. Okay, well, that concludes this example. I hope it was really helpful to see this process of how to move from a conceptual description of a process as we are developing an algorithm, and then use a flowchart as an intermediate step, and then finally actually implementing the code. And I hope that going through the code in some detail here, actually using some of the debugging capabilities of Matlab, was useful. And if you have any questions, please come and visit during office hours. Thank you.